Hi everyone. Thanks for coming to the Spark training today. We're going to get started. So we have pretty interesting schedule ahead of you with overviews on both Spark, Shark, and Spark streaming. And as the first speaker, I'm glad to introduce Pat McDonough. He recently joined Databricks, just like everyone else at Databricks actually, and he's going to talk about Spark.
All right. Good morning, everyone. Good to see such a large crowd. I think everyone was really very pleased with the turnout yesterday, and so let's hopefully carry that trend forward with a solid day of tutorials. We have quite a bit of information throughout the day. As Matej mentioned, there's several talks. We structured today with mostly tutorials up front and then hands-on afterwards. A couple of housekeeping things. First of all, if you're kind of in this middle section and you're worried about your ability to see the screen and see fonts, you'll notice there's a TV back there. So it might be worthwhile moving back a few rows if you're having trouble seeing. Later in the day, and actually you could go to the second room right now most likely, but it's more important later in the day when you want a table to use for your laptop. So we have a second room downstairs that's broadcasting the tutorials, and so you can feel free to go down there and take the train from that location. Any other housekeeping? I think that does it for the housekeeping. We will do, after the tutorial talks, we'll take a minute to make sure everyone has internet connections, but if in the meantime you want to kind of test out your connections, make sure you're all set up so that when the hands-on exercises happen, you're all ready. That would be a good idea. Okay, so first things first, I think we saw a lot of excellent presentations yesterday about how people are using Spark, what they're doing, a lot of exciting things going on. But chances that you could have seen some of those talks and perhaps don't know where the resources are for Spark itself. So first things first, you should know that our website, or not our, the Apache Spark website is an Apache incubator project. So that's the primary project resource, is to go out to that page and get started there. The code is hosted on GitHub, very active community. And obviously there's a user mailing list too, which is very responsive. Quite a few people are active and very helpful, so feel free to use that as well. One of the first things you'll notice once you go to the website is that the contributions in the community are pretty outstanding. You can see from this chart that I borrowed from the GitHub repo that over the last 18 months, contributions have been we've seen quite a few contributions, and we obviously at Databricks intend to make that trend continue. But the community extends far beyond just Databricks and AmpLab. You can see the kind of NASCAR logo display down there. If you include all the people who have contributed in the past and all the people who maybe sponsored this conference or gave talks or are just active on the mailing list, it's pretty exciting to see the community that's forming around Spark. But with that said, it can always be bigger. It's very much inclusive, and we want everyone to get involved. So after today, once you're comfortable using Spark for writing applications, feel free to jump in and provide contributions. Actually, yesterday, when Matej put up the slide of all the prior contributors, it was funny. I was sitting next to someone who said, "Hey, my name's on the slide. It's kind of funny. I submitted a contribution about 2 years ago. It was like one line of code. It was insignificant, but the truth is, and nothing's insignificant. Any contributions help to grow the community and make Spark a better project. So please do get involved, critique the docs, one line of code, whatever it might be. Okay, let's start out by talking about the core concepts of Spark. Later on, we will also get into some specifics about a lot of the API. And then we'll do a little bit of a demo to demonstrate some of that stuff. Again, if we're moving too fast, just remember that you're going to have a chance later on today to do some hands-on exercises and touch all this stuff yourself. So hopefully that will suffice. So first of all, what is Spark? Again, you saw a lot of talks yesterday about how people use it, but how do we define it? And most often we define it as a fast and expressive cluster computing system. Compatible with Apache Hadoop, so it's fairly frequently deployed alongside or on top of a Hadoop cluster. And we aim to provide efficiency and usability. And so the efficiency comes from general execution graph. So implementing a general execution graph of operators, which you'll see later helps to optimize certain performance aspects. And then fast in-memory data sharing. So if anyone's spent 10 or so minutes with Spark, you've come across the term RDDs, or resilient distributed data sets. It's a fundamentally core concept of Spark, and you'll see a bit more about that as we move through. And then second of all, usability. So we want to provide tools and APIs that make Spark easy to use. So it can do a lot of powerful things, but we don't want to make it overly complicated like other APIs you've seen in the past. And then as far as usability is concerned, another important aspect is having the interactive shell, which again gives people the barrier to entry to getting started on Spark is very low. You can jump in the shell and interact with your data right away. And fortunately, we've seen that this has worked very well. So as far as efficiency is concerned, we see certain applications go up to 10 times faster when reading from disk, but obviously much faster than that when pulling data out of memory. And this is as compared to Apache Hadoop MapReduce. And then second of all, as far as usability is concerned, we often see 2 to 5 times less code. So you'll see some examples in a little bit where implementing word count in Spark is a couple lines of code, very easy to understand and reason. As compared to Hadoop MapReduce, it's very concise and usable experience for the developer. So the key concepts behind Spark. So effectively, when you're working with Spark and writing applications or interacting in the shell, the API gives you the ability to program in terms of performing transformations on distributed data sets. And so fundamentally, the most important concept, the core abstraction of Spark is resilient distributed data sets, or RDDs. So RDDs are effectively a distributed data set. It's pretty self-descriptive term there, but they are a collection of objects spread throughout the cluster. You can control the storage aspects, so they could be stored in RAM. You could choose to cache them, or they might represent data that's actually on disk. They are built through parallel transformations, and you'll find that you often chain these transformations together. So RDDs actually contain lineage referring to prior RDDs, and that helps us in terms of resiliency. And that's the last bullet point there, is that they actually are automatically rebuilt upon failure using that lineage. And on these data sets, we perform operations. So operations come in basically 2 flavors. Transformations, so you might read from a file, and then the first thing you want to do is often to maybe parse out certain fields or filter it or do both or whatever. So we take an RDD, we perform an operation on it to transform it. So maybe that's a map or a filter or whatnot. And then actions. So actions are when you want to actually pull a result out of your data set. So I finally have filtered down my data set to the records that matter to me. Now I simply want to count them, right? So that's an example of an action. So here's a kind of a mental working model of how this all works. So typically, the first thing you do is to create an RDD. And so in this particular example, we're simply creating an RDD out of a text file, some file.txt. And then, as I mentioned previously, you often perform transformations on those RDDs. So in this particular example, we are looking to filter our first RDD for only the lines that contain Spark. So we send a simple Python function, filter it out. It creates a new RDD, which only contains the records that match my filter. You often do a couple of these, right? So you might do a filter, like I said, you might parse something. You might perform a map operation so that you send a function out to all of the elements in the collection to perhaps perform a calculation or transform them somehow. And then finally, when I want to pull out a result, I perform some sort of action. So here's a couple examples. In this case, I'm counting, or maybe I just want to kind of take a quick sample of the RDD, so I call the first action or operation, and it shows me the very first line. So it's kind of this is the working model to keep in your head. So you're creating RDDs. From that RDD, you're often creating other ones, transforming into other RDDs, and then finally causing the system to provide you a result by calling an action. So let's go into a longer example of log mining. So what we're going to do here is pull in a log and then do some kind of filtering and counting to locate specific errors and see perhaps how many MySQL errors are happening in the system or whatnot. So we have a small cluster here of 3 workers, and then we also have a server where our driver program is running. So this might be kind of a client computer, if you will. And we start by, similar to the last example, pulling in a file and creating an RDD that we're calling lines. So you'll note here that that Spark is compatible with HDFS. So as I mentioned, most often it's actually deployed in conjunction with Hadoop, and so you're frequently actually pulling files out of the Hadoop file system, and then it creates the lines RDD. So that's the base RDD in this example. So first step, we're going to filter out that RDD so that we only find the lines that contain the string error. And so what you see here is that, first of all, I'm taking my lines RDD, I'm calling my filter operation, and what I'm going to send in there is a function. So this, by the way, I should mention, this particular example is in Python. There's support for multiple languages, but throughout the presentation, we're going to stick to Python for the most part. And what we're doing here is, for this filter operation, we're sending a anonymous function. So if you're not familiar with Python, this lambda syntax is how you define an anonymous function. With the parameter s, we're going to basically do a simple string operation. Does it start with error? Okay, that's it. So that function in here will be sent out to the cluster, and the records that pass that condition will end up in our filtered RDD of errors. So that's the transformed RDD. Next thing we're going to do is take our line of log messages. So we found all of our errors. Now we want to kind of get selective about which data we pull from those lines. So not all the information is relevant for this particular search, and so we are going to use the line, or use the errors RDD, which we defined back here. We're going to call the map function, and we're going to send this anonymous function to each element of the RDD. And effectively, all we're doing here is taking the string, splitting it by the tab delimiter, and then pulling out the third element of the array. And so this creates a new RDD of messages, where we basically have just pulled out the third element of that tab delimited line and created a new RDD called messages. And finally, we know that what we want to do is do a couple of different operations on that RDD. We might use that for our kind of exploratory analysis, mine that data, do a number of different things. So we know that it makes sense in this particular case to actually cache that data so that we're not constantly reading it from disk. So you might notice that throughout this example, as I've been moving through the different lines, that this is an animated slide, and you haven't seen any animations yet. And that's intentional, because all of the transformations that you perform on RDDs are lazy. And there's good reason for that, because that gives the scheduler an opportunity to optimize them. So for example, in this case, when I called filter and map, I don't want Spark to go and read through these blocks of data twice, once for filter and once for map. I want it to combine those into a single stage of execution. And so by being lazy, by lazily executing against the operator graph, it can optimize that by effectively just reading that block once, doing filter and map in a single stage, and there you go. Okay, so finally, we actually called another filter here, similar to the one before. We're going to just, in this particular case, only find the MySQL errors. And finally, we've actually called an action called count here. So this actually causes Spark to have to provide results to us, and so all of the lazy operations that we've been waiting on are going to execute now. So let's look at how that happens. So this is HDFS data. HDFS, as you're probably well aware, is a distributed file system, and so the blocks of data are spread through the cluster. Spark is locality aware. It understands which nodes hold which data, and so it's going to send tasks out to each of the workers, and each of the workers is going to operate on its particular chunk of that data. It's going to stream through the blocks, so all of this initial stuff here, the filtering and mapping, is going to happen as it's streaming through the data and creating these RDDs on the fly. And then because we called cache, as it's filtering results and deciding which ones pass these conditions, it will go ahead and cache them on the different nodes in the cluster, and finally return my results. So this is great. I've now streamed through all the data. I've filtered it. I've set up a cache that I can use later, and I've also got my result of how many errors there are. Now I want to do another analysis here. Instead of looking for MySQL errors, I'm looking for PHP. So basically very similar to the last line of code here. I'm going to run another filter with a different function. It only differs by which term I'm searching for. I'm going to run a count again. And this time, as that action is executed, because the data is cached, it's not going to stream through the blocks of data, right? That's the point of a cache. It's going to access the data in the cache and return my results. And so where the first filter and count would have taken the time to read the data off a disk, the subsequent executions are very fast because the data is just in memory. So this is obviously a very useful concept, and so as you're doing this kind of data mining where you might continue to access this same cached data set, you can see some significantly faster analysis than as compared to writing Hadoop MapReduce jobs over and over again, as you might expect. And in fact, we've seen on, for example, a full text search of Wikipedia, which is about 60 gigabytes of data on 20 EC2 machines, very similar to the demo we'll do later. We can see those subsequent filters on your cached data execute in about a half a second versus, of course, about 20 seconds for reading from disk. So it works and works well. And also, a lot of people, the first question they ask when you start talking about is how RDDs are cached is, what happens if not all the data fits in memory? So it does degrade gracefully if you don't have enough memory to cache everything. You can see the performance obviously is a bit slower if you don't have any cache, but it still is able to understand which data to cache and which ones need to be streamed from disk. Another important concept for Spark is I referred to it before, lineage. So as we are creating these operations against our RDD, so in this case we start with a text file, we run the filter and then the map to create our messages RDD. Spark keeps track of the lineage, and so I mentioned that helps us, first of all, to optimize which operations we execute when, but it also helps us, importantly, for fault recovery. So in this particular case, my messages RDD is the one over here on the right, the mapped RDD. Spark knows that mapped RDD actually came by running the split function on the filtered RDD, which came by running the filter function, or by running, starts with on the actual file RDD. And so if I lose a node in the cluster and lose the blocks of data, or the partitions of that RDD on that particular node, it can isolate the rebuild to only the partitions that were lost. So it uses the lineage to help recover quickly. Okay, so I mentioned that all the slides that you'll see here, for the most part, are Python, but the API is available also in Scala and Java. There are obviously differences in terms of syntax. I mean, Python and Scala look very much familiar. With Java, the challenge is how to give people a concise way to define anonymous functions. And so Spark has done a pretty good job of keeping it concise, but obviously if you use Java, it's going to be a little bit more code to write as far as characters. But that is certainly available, and if you're familiar with Java, maybe that's where you start. However, with that said, chances are when you first pick up Spark, you're going to be immediately using the shell. And so keep in mind there are basically two shells available. There's the Python shell and the Scala shell. If you're not familiar with Scala, it's okay. I mean, Scala is basically a JVM language, and so you can actually write a lot of Java code in there. So that's probably your first stop if you're a Java developer. The standalone program, so I just described using a shell, which we'll see in a little bit, but you also, of course, might write an application that you deploy somewhere, and for that type of program, you can use any of these APIs. And then one note about performance is that because it's implemented in Scala and because Java and Scala use static typing, some of the performance can be a little bit faster in those languages, but typically it's not going to be a significant difference, and you should feel free to use Python, and that's something we'll continue to look to improve over time anyhow. So just mentioned the shell, but this is by far the fastest way to learn Spark. I mean, you can literally get started in Spark if you just are interested in the API by downloading the project, unzipping, and then going to the shell, and you're there, right? And maybe you're not working with HDFS or scheduling jobs on a cluster or anything, but you can start playing with the API and learning the syntax, et cetera, that quickly. So I just mentioned it's available in Python and Scala, and the shell itself actually kind of runs as an application in Spark. So I'll show you a little bit about that later. Excuse me, let me clarify that. So if you have a Spark cluster, the shell will run as an application on that cluster. However, you can also run locally by not pointing to a cluster manager and simply telling it how many threads to run, and then it's going to run an application right there locally on your machine. Spark also has some administrative GUIs that are important to understand. So the very first stop, if you're curious what's going on with your cluster, is the so if by the way, there's a few different deployment modes which you'll learn more about throughout the day. This particular example is if you're using the standalone mode. So standalone is basically a kind of lightweight built-in cluster management framework. And if you happen to be using that mode, this is like the master page, the Spark master GUI. By default, it's hosted on port 8080. And this is where you would find how many workers are up and then which applications are running. So in this particular case, you can actually see right here, the name of this application is Spark Shell. So when I created a shell, it's actually represented as an application in Spark. It's taken resources to execute the operations you're going to send to it, and it's viewed as, this is an application. If you were to follow through to these links here, you would end up on a application page, which gives you specific information about what's going on within your application. So you could see in this particular example, well, if you can see, hopefully you can, that the last couple things to run were reduced by key and account, and et cetera. So this is where you would kind of dive into your app and figure out what's active and whether things are up and whatnot. Okay, let's talk a bit about job execution. So as I mentioned, when you launch an application, you have the option of either connecting to a cluster manager, requesting some resources, and then working with the resources that are available, which in the last screen where you saw those here, these are called workers. So if those workers are available, I can give Spark the opportunity to schedule my execution across the cluster. But if I'm just maybe testing something locally or just playing with the API or whatnot, I can basically choose to not connect to the cluster manager and instead connect to local or just create local processes. So as far as cluster managers are concerned, I just talked about the standalone cluster manager, basically what we call standalone mode in Spark. But there is also Yarn and Mesos cluster manager available. Well, I should say Spark is compatible with both Yarn and Mesos as well. And then as you saw, most of the examples start by grabbing data from a file. So maybe that's HDFS, maybe it's a local file system, whatnot. And your Spark has access to all of those different types of resources. And if it is HDFS, you'll see some APIs later which show you that you can, just like any Hadoop client, you can use a bunch of different input formats and whatnot. So here's a good example of what scheduling looks like in the cluster. I mentioned some of these things earlier, but so it's a general task graph, and it optimizes execution by pipelining certain functions. So in this particular case, you can see the execution graph included basically a map and a filter against the same RDDs, and so it's able to actually pipeline these into a single stage, as I mentioned earlier. You'll also see that it understands locality and it is partition aware. So in this particular case, this RDD was already hash partitioned. And so as it goes to join this RDD to this one, it understands that it doesn't have to shuffle this data across the network. It's already been partitioned, and to do the join, it only has to shuffle this half. And so these types of optimizations are part of the reason Spark is fast, obviously also because it's accessing a lot of this data from memory. That these black boxes kind of represent cached data. Another thing to be aware of is it understands when it cached data, right? So it knows that it doesn't have to rebuild this RDD because it's already been cached. It doesn't have to go back here and stream through the data to create this RDD to subsequently join to this one. So there's a lot of optimizations under the covers, which, by the way, as a developer using the API, you don't really have to worry about this stuff. It kind of just works, but it's good to understand how that comes into play. There's also some advanced features. If you're interested in these, definitely check out the docs, but you can have some control over partitioning, and you can actually control the storage formats. So you might want to change how it's serialized or whatnot. It's up to you. Shared variables for broadcasts and accumulators, definitely go check it out if this stuff is something that you're interested in. Again, the Spark page is an Apache incubator project, and there's great docs on there, so I definitely encourage you to check those out. All right, so if you want to start working with Spark, which is what we're here for today, first thing you're going to do is probably launch the shell. And so there's effectively two shells available. There's Spark shell, so this is inside the project directory. At the root of that directory is Spark shell, which is a Scala-based shell. And then there's PySpark. Highly recommend using the IPython equals 1 environment variable, which will allow you to use IPython, which gives you conveniences like tab completion and searching your history, etc. And then, as I mentioned before, you have the choice of what mode you want to launch. So if I want to run locally, I actually don't have to pass anything at all. That'll be the default. If I want to control how many threads I want to run locally, then I might use this syntax here. I'd say set my master variable and say equals local with a number in here, which corresponds to how many threads you'll run. But if I have a cluster available, certainly I'm going to want to use that. And so you connect to the cluster by sending in your URL into that same variable right there. Once you get into the shell, conveniently there's a Spark context that's already available. If you happen to be writing an application, you need to create that on your own, and we'll have some slides in a bit to show you the specifics there. But that is, it's important to understand that once you jump into the shell, you'll have the SC, the Spark context, is set as the variable SC. And so that's going to be your first stop. You probably saw that in some of the previous examples, sc.txt-file, etc. Right? So that's your first stop to create RDDs or maybe look at your environment or whatever it might be. Okay, so let's talk about how to actually create RDDs further. We've seen some of these functions already, but this gets into a little bit more detail. So for these examples, we'll use this parallelize operation. And really all that does is take a local collection, in this case a small array of 3 values, and turn it into an RDD. So really useful for examples like this, where we can say, okay, the first thing we're going to do is create an RDD that has the values 1, 2, and 3 in it. Okay, so you'll see that in a little bit. Also, as I mentioned, text files here, so you can access local file systems. You can access HDFS. It supports any HDFS client URL, URI string. So including you can put stars here and grab all the files in a directory, for example, and put those in a single RDD. And then, as I mentioned, there's ways to customize which input formats you're using by this syntax here. So the basic transformations, several of these you've seen already, but in this particular example, we're going to create this array, 1, 2, 3, create an RDD out of this array called nums. And so we'll just walk through some of the basic operations you might use to work with this data. So in the first example, we want to create squares out of those 3 elements. So we, again, use the map function. So if you're familiar with functional programming, this is very common. And all map is saying is for each element in the RDD, please send this function in there and give me the results. And so for nums, we send in the, again, this is Python anonymous function, and we just square the value and return a new RDD with squares. So that gives us 3 different elements, 1, 4, and 9. A filter operation, I think we've done several of these examples, but in this particular case, I'm going to set up my function to isolate, to return only even numbers. So I write a function here. The filter operation executes the function and creates a new RDD, even, based on the elements that pass that function with true. Finally, probably the more complicated example on this slide is flat map. And this is pretty common here. So in this particular example, you'll see that my function actually returns multiple results per line. So for example, if you're not familiar with range in Python, effectively this gives me all the numbers leading up to x, right? So for 1, it returns 0. For range 2, it returns 0 and 1. And for range 3, it returns 0, 1, 2. Right? So every time I execute this function, if I called map, I would have an RDD of arrays. But often for this type of, often you'll find that you want to flatten out that structure. You don't want a matrix, basically. You want to take all of the elements in a particular you want to take all of the elements from the array and flatten them out into a single RDD. And so that's what the flat map operation gives you. So you end up with the result of 0, 0, 1, 0, 1, 2, right? Okay, so that explains the range one. So let's actually go into a little bit of a demo here and cover some of these things we just talked about. So you'll see here I actually have a Spark Master. This is the Spark Master GUI, as I referred to before. And it's got a few workers available. This is pretty small font, but basically all you need to know here is that we have all these different workers. And then down here we have no running applications. Is that true? No, that's not true. We do have this one running application, which is my Spark shell. So actually I'm going to go ahead and quit out of that and show you that if I do that, you'll see that my application is now gone. So there's nothing really running on this Spark cluster. I've got these resources available, not doing anything. I'm going to go ahead and use those resources now. You'll see I'm going to use the PySpark shell. So let me see here. Try to make that bigger for you guys. So I'm going to call the PySpark shell. And actually, before, it's worth noting, remember in the last slide I said that we highly recommend using IPython. And so prior to this, I set the environment variable IPython equals 1. And that's going to say when I run PySpark, please use IPython, which gives me things like tab completion, et cetera. And then I want to, when I call PySpark, I'm going to send in my master URL. And that happens to be located, this is, I use the EC2 scripts, so there's some great EC2 scripts available. You'll find them on the project website, which basically set up a cluster for you without having to do a lot of work. That's what I did here, and so my master URL happens to be available in this config file here. And so that will be set as the master environment variable, and then when I run PySpark, it's going to go ahead and connect in to that particular cluster. So you can see all of the different workers basically registering. And if I go back to my GUI, you'll see if I refresh this page that there's my application. Okay, so now we have an application, we have some resources available to us, and we are going to start doing some work here. So first thing I'm going to do, go ahead, Gus.
Do they have to actually keep a particular sequence of starting the cluster, like master first, then workers, or it doesn't matter?
So there's an operations talk later that'll get into all the details for that. So yeah, one of the talks after this and then Shark is about kind of how to operate a Spark cluster, and we'll probably address those types of things then. Now, as far as the EC2 scripts are concerned, it should just work, right? So they basically, you run one command, it spins up a bunch of nodes, and magically you have a cluster, which is great. Yep. So first thing we're going to do is actually pull a file out of HDFS. So this is actually going to be a search. What we'll do here is kind of search through some Wikipedia text. And Wikipedia is about 60 gigs. It's not really that big if you think about all the text in Wikipedia, but clearly that is a kind of a big data problem. So let's go ahead and use that as our example here. I'm going to, since the HDFS URL can be a little bit long, I'm going to go ahead and just pull it out of history. So again, I'm using IPython, and that gives me the chance to just search my history and easily pull out past commands. And what we're going to do here is create this variable, not variable, pardon me, an RDD called wiki, which is going to use the Spark context, SC. Yes? Sure. Well, if I hit enter, it's going to execute here. But you know what I can do is let me just not be in full screen. Does that help? Okay. Even more? Okay. Thanks for saying something. Okay. Sure. So let me actually cancel that. Okay. So let me get back to where we were there. So I'm going to basically pull this file out of HDFS. I'm going to create a new RDD called wiki. We're going to use the Spark context. So actually, before I even do that, let me show you a little bit about the Spark context. So Spark context, there's not that many interesting things to note from as far as variables that the Spark context provides you to look into. But just to kind of, again, prove a couple things here. First of all, this is tab completion, which is really nice to have. And you can see, for example, if I were to maybe just do sc.master, it's basically going to tell me, okay, this is the master that this Spark context is connected to. So this is kind of the starting point of any program or the shell or whatnot as the context. And then from here, I'm going to use my context to pull the file out of HDFS, as I mentioned. So creating wiki, I'm grabbing, this file has already been kind of transformed a little bit to help us with formatting and whatnot. It's also worth noting that I could have not used the full syntax here to grab that file, but that's fine. So this cluster is set up, this client is set up to, by default, use HDFS, and I could have skipped all of that full URL, but for illustrative purposes, I wanted to give that to you. So I created that RDD, and obviously, again, because everything operates lazily, clearly it didn't actually read 60 gigs that fast, right? But it's basically created this representation of an RDD for us. And what we want to do with the wiki RDD is basically, I think the first thing we'll do is just take a little sample. So we're going to use the take function, which basically takes the first element. Whoops. So we're going to see what this data looks like. And you can see that, well, it's hard to see because we have such a small screen, but it's basically a tab delimited line of XML data. It has some metadata available, and it also has like a free text field at the end. So I happen to know from working with this data set that the fourth element is just the free text, no XML tags or anything like that, and that's the one we want to work with. So what we'll do is go ahead and filter out that data, or the other fields, pardon me. So we're going to run the map function on the RDD, and we're going to create our lambda, which says takes in line as a parameter, and we want to split it with the tab, and then take the fifth element of that array. So I forgot to set that as an RDD, so let's go ahead and, I did that wrong, sorry. Wiki text equals wiki.map. Is that right? All right, let's see what happens. Nothing happened. Yeah, I should have seen some output though. Yeah, thanks. That take one. That didn't work. Bear with me, sorry. Let's go back here to where we were. Oh, sorry. So I set, you see what I did there? I set take one into wiki text. So part of what I meant to do is actually basically test my split right here. So what I wanted to do is split by tab and then see the fourth element and take the first one just so we can see if that's correct. So excuse me there. And you can see basically right here, this is, so the fifth element of that of the line there is actually the free text, which is what we want to use to do our analysis. So, okay, that sounds good. So now what I do is instead of just taking one, I'm going to go ahead and set the, create a new RDD out of that. Okay, and so now let's whittle this down to the data that we really want to work with. So I'm going to basically do some analysis on articles about football, right? So I'm going to go ahead and say, why don't we filter this out with the lambda of text, and we're going to make sure football in text. And again, let's just take a quick little sample to see if this makes sense. All right, so we don't have a lot of screen space here, but I kind of look through this and say, okay, that's probably about right. So that now, obviously, I was actually talking about American football, and this seems to be English, and so it's probably soccer, but that's all right. We'll ignore that. I hear some British accents saying that's just fine. Okay, we'll call this Football Wiki. Okay, and whoops, actually, you know what I really want to do? Since we're going to work with Football Wiki, we're actually going to do the same thing I just did before, which is kind of hard to see given the small screen, but we're actually going to cache it because I'm going to do a couple different things against this RDD. I don't want to be streaming off of disk over and over again. All right, so Football Wiki is the cached data set. Now, obviously, this is lazy, so it didn't just read 60 gigs of data. In order to trigger some sort of actual read of the data, we have to perform an action, right? So let's go ahead and say footballwiki.count to see how many articles we're going to work with here. Whoops. Okay, so now it's basically reading through all the data, and this is going to take some time. In fact, I ran out of instances on Amazon last night, so I was only able to provision 15 nodes. Typically, we would do this demo with about 30 nodes, so this is probably going to take about 2 minutes, but that gives us a chance to go through this GUI here. I am going to expand the size here so you can actually see. So as I mentioned before, this is the master page. This tells us how many workers are alive. So you can see there's 15 there. You can actually filter these fields. These are all sortable, not filter, pardon me, sortable. By clicking on them, everything's alive here. These guys all look very similar. And in this particular case, we want to find out what's going on in the application that's running right now. So I happen to know that it's pretty easy in this case. There's only one application. If you had multiple applications running, perhaps they would have different names, and that would tell you which one is yours. So let me go ahead and click on this application. This application tells us which executors are available to this app. So keep in mind on the last screen, let me go back here. On the last screen, these are workers, so these are basically kind of lightweight daemons running for the Spark cluster. That differs from executors. Executors are actually processes that are doing the work on a worker, if that makes sense. And so I can see in this particular case that this application has all of these executors available. And if I go into the actual detail of this app, I can see that we are in the middle of this stage right here, the collect. So collect is basically bringing all the results together so it can run a count. I can also see if I go over to this tab, the storage tab, that because I chose to cache this RDD, it is in the process of doing so right now. I'm almost done here. I'm at 98%. And if I get to 100, you'll be able to go back to the terminal, and we'll have our results. So let's see how far are we? 469 and a 480. So we'll give that a little bit of time. We'll come back to that in a second, and move on to the next page for actions. So I forgot to cover these before I got into the demo, but you've seen most of these used. So collect would be basically a way to bring the RDD into your local shell or application. So you noticed from the Spark GUI that's effectively what's going on with the demo that I just ran in order to count the elements in that RDD. You saw me use take, so take is pretty simple, right? Just give me the first couple elements in the RDD. Count is fairly self-explanatory. Reduce is a pretty useful operation. Basically, you give it a function that says how do I take two elements and reduce them, right? And so often that you might be creating a sum. Like in this particular case, I take my two variables my two parameters, x and y, and just add them together. So from this RDD, I'm basically saying, okay, we're going to do a reduce. It's going to reduce these three elements, 1, 2, and 3. The way to reduce it is to run this function, and so as it reduces all of those elements in the RDD, we get the result 6. And then finally, save as text file. Very much self-explanatory, but often we're going to put our output into an HDFS file or local file or whatever it might be. Okay, let's see if our job is done here. So that says it's cached. Pardon me, I lost my terminal here. There it is. And we could see that in this RDD, we have 237,000 elements in the RDD. So that's basically how many articles there are that match football. And what we want to do is kind of perform some analysis here. So actually, I'm really kind of curious here. Let's see, from the football wiki, let's find out how many articles contain, let's see, article contain Raiders. Let's find out. 100? That can't be right. I meant to capitalize it. Okay, 3,000 something. So that's good. Now let's go back to the GUI real quick and see that whereas the first execution to read the data from disk took about 3.5 minutes, which hopefully you can see that, but that's basically what I'm highlighting here. The subsequent searches on that same data set are now in the 2-second range because it's all cache, which is fantastic. Yes? The majority of could you repeat that? Yes. The time is mostly from streaming the data from reading from disk, basically 60 gigs from disk on my 15 nodes. It has to pull that into the cluster. It had to filter and map them and then cache them, right? There are 15 worker nodes. That's correct. Yeah. And obviously the subsequent operations are using the cache, and so they don't need to go do that stream. Good.
How much is the overhead per object? Is it basically beneficial to have smaller objects or like big ones? Like lines are big versus
Right.
you just storing one in.
Yeah, well, I mean, if you want to cache your data, then certainly you are limited to the size of the cluster. And so if you have a large data set and you want to fit it in cache, and perhaps you would trim out certain values ahead of time. Does that make sense? Yeah. Okay, so that was interesting. Fortunately, we can see that because we're cached, we can run a lot faster. We got our 3,000 articles. Curious though, football wiki dot filter. Let's do another analysis here and compare them. Let's see, 49ers. Let's find out what this looks like. All right, we got our result very quickly. 2,000. Wait a minute. Does that mean there's more Raiders articles? It does. I'm a Raiders fan, so I'm happy to see that. There you go. So that's a good, like, very simple example, just filtering through data, performing some counts and whatnot, working with a decently sized, fairly large data set, and basically doing it a lot faster than you would if you didn't have access to cache. So that's great. Okay, let's go back into the presentation here and talk about some more operations available to you. So very often you're going to work with key value pairs in your programs, and so if you're using Python and Scala, this stuff should be pretty easy to understand. These are kind of built in and commonly used. But if you're using Java to write your application, you should be aware of this tuple2 class, which you'll use to create tuples. And these are the ways to pull the values out, is the _1 and _2, so that it has a very familiar API, just like the other languages. And so if you're using these key value elements in your RDD, there are some special functions available to you. So first of all, in this particular example, we're going to create an RDD of these key value pairs. So we're taking stock of who has how many of each kind of pet. So the first person has 1 cat, second person has 1 dog, and the third person has 2 cats. And so we can use the reduce by key operation in this case to do exactly what it sounds like. We're going to do the similar reduce operation that we ran previously, but it's going to do it by the key of the tuples. And so in this particular case, we see that cats have 3 total, right? We reduce the cats into 1 element, and we reduce the dogs into another one. So that's separated by key, self-explanatory for the most part. We can also do a group by key. So in this particular case, it's fairly simple. We just call group by key. It creates a new RDD, which groups the cats and gives us all of the different values for the cats. And we group dogs and gives us all the different values for dogs. And then finally, sort by key, which is pretty self-explanatory. It's just going to reorder the elements of the RDD to create a new RDD that's sorted. Reduce by key also automatically creates combiners on the map side. So if you're familiar with Hadoop MapReduce, that's an optimization that happens automatically in Spark. All right, so pulling it together here, let's look at what word count looks like using Python in Spark as compared to what it might be in MapReduce. You'll note that this is quite a bit less code, which is great. So I'm sure pretty much everyone in the room is familiar with what word count does, but basically we are going to take our lines of text from the Hamlet text file. We're going to split it by spaces, so we end up with words. We want to use flat map because, again, that would end up in an array of different words, and we want to flatten them out into a single RDD. Our map function is very, very simple. We're basically creating a tuple that has the word, which is this parameter here, and the value of 1 for each instance of this word. And then we go ahead and reduce by key, where the key is the word itself. And obviously, the reduce function is very simple, x plus y, and that's how you do word count in Spark. Pretty clean and easy to use API, a lot less code than what you might have done previously. A couple other ones real quick. So we talked about parallelize at the top there. Actually, that's actually part of the example here. So we're basically going to create 2 RDDs here, visits and page names. So obviously, these are kind of related, and if you think of this as maybe like a database table, clearly there's some opportunities to join these data sets at times. And in fact, that's what the join operation does. So basically, we take visits, join that to page names, and that gives us a joined RDD where we have it, where we have the page name here, or excuse me, the visit key here, joined to the page name and the IP address the visits came from. And then if you're familiar with cogroup, the cogroup operation from PIG or whatnot, we have that available as well. There's several other operations you might want to get familiar with in the pair RDD classes on in the documentation. For all of these pair RDD operations, you can pass in an optional second parameter, which sets the level of parallelism, so basically how many tasks you're going to run when performing those operations, so keep that in mind. So all the ones I just showed before, you could have passed in this optional parameter to explicitly define how many parallel tasks you'll run. Some things to think about is using local variables in your program. So obviously, if I want to, for example, create an application that takes some user input on the command line and pass that into the program, keep in mind that obviously there's a new copy of this variable as you execute the application throughout the cluster. So obviously Spark's API is like really easy to use. It makes your applications kind of look like they're not distributed programs, which is the nice thing about it. But don't forget that it actually is a distributed program. So it's not like if someone in your app sets a new value in query, that's going to magically reappear in your application. This is a new copy of the variable out in the cluster. Also, because this is executing distributed functions, the variables you use need to be serializable in Java land or pickleable in Python land. And definitely don't use fields of an outer object. For example, in this particular example, we've created a class, my cool RDD app, set some variables up at the top, and then in our map function, we use this parameter here, which was defined as a local variable. So this is a problem because either my cool RDD app might not be serializable, or because we've basically used an inner variable of a class, of an object, we have to actually serialize the entire thing. So maybe this whole class is not serializable, maybe log is not. Clearly, we don't want to be doing that type of thing in most cases, right? So it's easy to get around, though. Basically, instead of using the variable from the object, you can basically just set a local variable and pass that. So I just set this param underscore to take the value from param and then pass that in. Easy to fix. Okay, so there's several other operators available. Obviously, we've moved along we've moved past just having map and reduce available to you. The list is pretty long of what you can use in the API. We've covered a lot of these. There's more available in the docs as well. Is there a question back there? For any object that you... Oh, so the question was, is this example specific to Scala and Java? And this obviously is written in Scala and Java, but same case for Python as well. If you're going to access a variable of an object, we have to serialize the whole thing. If that makes sense. Okay, so we've done a lot of examples of using the shell, but obviously there's cases where you actually want to deploy kind of a standalone application. At the end of the day, working with Spark is basically just a jar. So you can add the Maven dependency to your project like so, and you're off to the races. In Python, you want to run your program with the PySpark script. And as I mentioned, the shell makes it really easy to work with Spark because you have a Spark context for free and you're just kind of up and running. If you are creating an application, you're responsible for creating that context. So the variables in that context are, for example, the cluster URL, the name of your application, which again you saw in the GUI. The name of the application I was running was PySpark shell. Where the libraries are on the cluster, and then other jars that you want to ship with your application. So that's what it looks like in Scala at the top. This is what it looks like in Java. Same thing basically in Python. And the complete app. So we showed you the code for the word count example previously. This is what a full app might look like. There's only more or less one extra line plus your application code for creating an application on the cluster. Okay, so you know what? Unfortunately, we don't actually have time to go through this example. It's 10 now, and I think we need to move on to the Shark talk. But if there's any other questions, maybe Matei, you want to come up and we can take them from the audience? So anyone have any other questions before we move on to Shark? Go ahead.
Do you have a message to know in the RDD site?
I'm sorry, one more time?
RDD site. How big is the RDD?
How big is the RDD?
Yeah.
So I mean that.
Going to be good.
So the as far as like when it's cached in memory.
Yes.
it's as big as the data. Maybe, I mean, how can we describe how big the overhead is?
Yeah. So are you asking how? Sorry. Yeah, I can help answer these two. Are you asking how to find out how big it is?
Yes.
Yeah, you can look at that UI that Pat showed. Actually, he showed it.
If I read some kind of a script, I want to know it, in my program, how do I know that?
Oh, I see. There is actually an API for that on Spark Context also to find the size of it. I think it's called get stored RDDs or something like that. Get persistent RDDs.
Okay.
Yeah.
And you can see on the GUI for this cached RDD, the size is listed there.
Yeah, the GUI, I know.
Yeah, okay.
Do new nodes join into the cluster as they get added, and do RDDs get rebalanced, or do they stay where they are?
Yeah, so nodes can join and leave the cluster at any time. The question was, can nodes join and leave, and do RDDs get rebalanced? Currently, they don't get rebalanced unless maybe you schedule some work on them and the scheduler decides some nodes are not doing anything, so let's try computing them on those. So it doesn't automatically happen. You'd have to actually launch something to do it. Yeah.
Actually, I've got three questions. If caching is so beneficial, why not using caching as the default behavior when creating RDDs? Second question, if you've got many RDDs cached in memory, does Spark use any policy to kick partitions out of the memory? And the third question is, if you're creating an RDD from a data store and data changes inside this data store, what happens? Does Spark knows that this data has changed?
Yeah, so I mean,
Can you repeat the questions?
sure. Okay, so there were three questions there.
You guys share this one?
Okay, actually, there's a second mic right there. So there were three questions there. Why not always cache your data? So I think the answer to that is, if the data is too big to cache, then that kind of wouldn't make sense, right? So it really depends on your application. Typically, you want to be explicit about which data sets you put in memory and then subsequently access. So it's intentionally explicit in that case. The second question was, does the RDD get kind of updated in memory? Was that your second or third?
My second question was, if you got many cached RDDs in memory, does Spark use any policy to kick calculated computed partitions out of memory?
Right.
So, for example, like LRU.
It's
or
LRU. Yes.
It uses LRU.
Yes,
Okay.
yeah.
And the question is, when you created an RDD pointing to a data store and the data has changed from your latest analysis, and does Spark recognize the changes inside the data store?
So if it's cached already,
Uh-huh.
then you're going to have to recreate the RDD.
Okay.
So RDDs are effectively immutable, right?
Is there an easy way to tell Spark to recreate the RDD, or do you have to do it as explicit?
So that actually is probably a good way to answer your initial question. That might be a reason why you don't always cache everything. So you might set up your pipeline so that it's intentionally reading from disk for files that you expect to be updated, right?
Thank you.
Yeah.
Yeah.
So hi, my name is Neil. I wanted to talk about best practices for caching. So once you have done caching and read all the data, is there a way of keeping that cache there? Will it take care of that itself? When is the cache cleaned? And what is your advice on that?
Yeah, so the question was, yes, once you've cached some data, is there any way to manually manage the cache, for example, to remove data? So there is an API called unpersist on RDD, which lets you remove it from the cache. You can also often just rely on the LRU eviction, and in most programs, it's doing the right thing because the things you used most recently are the ones that stay.
Thank you. One other question I had
I have a question actually.
was,
Oh, okay.
sorry. So once you've maxed out your cache memory that you have available, does that cause any problems once you've exceeded that?
Yes, so yes, once you exceed it, old blocks or old partitions will be dropped from the cache in a least recently used fashion. So the program will keep running, and it will only have a subset of the data.
So this is the same as like garbage collecting?
It is. It's similar to garbage collection. Yes.
Okay.
Well, my question is just an extension of the last question. When the older partitions are removed by the LRU, is there a way to use page cache instead of going to the LRU and kicking the partitions out for the RDDs?
Is the question whether you can cache it on disk or what is?
Yeah, page cache.
Yeah, you can actually. So you can set in the cache API. There's an advanced version of the API called persist, where you set this storage level object, and that can be stored in memory only or memory and disk, or even just disk only if you want. Yeah.
My question. So in the Wikipedia example, we had 60 gigs of data on all the wiki pages, and we had 15 worker nodes. Each of them had 6 gigs RAM. So that was more than sufficient for that data. But let's say I have a 250 gig file. Like let's say the same file was 250 gigs, and I have the same 15 nodes with only 6 gigs of RAM each. And I invoke the cache operation on the RDD, what would happen?
So if you recall the slide that we showed where it can kind of degrade depending on how much memory, or excuse me, how much of your RDD is cached, effectively that kind of explains what will happen. So if you can't cache the entire data set in memory, it degrades gracefully in that case and will stream data from disk in the cases where it's necessary.
Okay.
Here, let me show you the slide again, just to make that clear. So that's what this graph was supposed to depict, is that scenario. Okay, so probably one more question. Okay, go ahead.
Hi, I was wondering, with the freedom to set the number of reduced tasks, what should I be looking out for in terms of have I overshot the mark, or have I have I oversupplied or undersupplied the number of reducers? What's the downside of getting wrong in either direction?
Yeah, okay, so this is a good question. This is how to set the number of reduced tasks or parallelism. So essentially, in most cases, unless you have very little data, you probably want at least one reduced task per CPU in your cluster so that they're all working in parallel. So that's kind of a lower bound. If you set it too low, another problem can be that the intermediate work for each reduced task is too large, and then that work doesn't fit in memory as it's running the reduced task. So you will want to increase the number so that the tasks are small enough that they can all be handled. And usually, if you aim it so that your tasks each take at least a couple of seconds, that's usually a pretty good number. If they're becoming much smaller than that, there are probably too many. Yeah.
All right, I think we should actually end questions here, just so we have enough time to get through the Shark Talk. So there's a lot more questions out here, I understand. Take them to Matej and Pat offline, please.
Let me just. And obviously, don't forget, we're going to have a chance to do hands-on exercises. We'll have several people available to address any questions at that point as well. So.